All right, so 5.7, interpreting graphs of linear functions. We've spent this whole chapter talking about relations and functions, and specifically linear functions. So we know a lot already about linear functions. This is sort of the final section where we kind of explore even just a little bit deeper the meaning of graphs and what a linear function graph can tell us. Okay? So in your textbook, this is the first little activity. They give you a graph and a little bit of background. So if you want to just look with me, you can. This is in your textbook. This would be on page 311. Okay, so Foundations of Math 10, pre-calculus here, the Pearson textbook, page 311. So it says this: float planes fly into remote lakes in Canada's northern wilderness areas for ecotourism. This graph shows the height of a float plane above a lake as the plane descends to land. All right, so here we have a little bit of a graph. You can tell that it's a function, first of all, right? Because the line doesn't double back on itself. Any vertical line that you could draw wouldn't intersect the graph at more than one point, right? So if we drew any of those lines, it would only touch the graph at a maximum 1 point. It is linear because all the dots, all the points, and the line itself is a straight line, okay? So the question is, and what we want to focus on is the meaning of where the graph sort of touches the axes, okay? So we want to focus on that a little bit in this lesson. So the first question you see in your textbook, where does the graph intersect the vertical axis? So here's the vertical axis, is the up and down, right? That's the vertical axis that measures for us height. So this is the height of the plane as it's coming into land, right? So where does this line intersect? At approximately what? What would you say? At approximately 1,000 what? 1,000 meters, okay? So 1,000 meters in height. That's very, very good, okay? So what does this point represent? If we're talking about this situation, what does that point represent? Any ideas? More than just 1,000 meters above ground. What? Give me some more detail. What does this mean for the question? Yeah? Is that where it started? Okay, well, it would be a good guess to say the start point would be here because there's no graph before it, right? There's no graph up here anywhere. And so would this be a start point? Yes, you're right, it's a start point. What about some more detail? Again, what do we know about the start point? Yeah? Okay, that's a little bit better. At the beginning, this is the plane's height as it begins its descent. That's great. Or when we first start measuring the plane's height, it's at 1,000 meters as it descends, right? So yes, all of that is good. This is sort of the beginning of the sort of situation, but this is, more importantly, the first point that we take. So I like that one, a full detail saying that this is the height of the plane as it begins its descent. And we know it's beginning, why? Because look at this axis down here. This is time, and this point right here is at what time? It's at time 0. So whenever you see a time 0 on the x-axis there, that's a pretty good idea that that's when this whole thing is starting. Okay? Very good. Okay, what about this point right here, where it intercepts the horizontal axis? What can you say about that point? And don't just say it's 10 minutes, because I can see that, but what about the context of the question? What's happening at 10 minutes? Yeah? Okay, so it took the plane 10 minutes to land in the lake. We're a float plane, it's coming down to the lake. Okay, good. Yeah, I like that. The whole situation here that we've been measuring takes 10 minutes. Or you could also say 10 minutes after we started taking all these height measurements is when the plane touched down on the lake. So either anything like that is great. Yeah, that's exactly right. See all the information we're getting from this graph? Okay, it took 10 minutes to descend. Okay, it started off at 1,000 feet. That's when we started measuring. It's awesome. Okay. Now, what about the rate of change for this graph? Do you remember us talking about the rate of change? What's the rate of change? And what's another word that we used for the rate of change of a straight line? Slope. Yes. So we're looking for the slope of this graph. Now, when we calculate the slope or the rate of change, what you can do is you can take any 2 points, and I'm going to take two different pairs of points. I'm going to calculate the slope. But what you're going to see is that the slope, if you use any 2 points on a straight line, should come up with the same slope. All right? Good idea, if you want, you can use the intercepts, which are, this point right here has a 0 x coordinate and a 1,000 for a y coordinate, right? So let's say point 1 is the point 0, 1,000, okay? And we're going to use this point right here. And I want to find the slope between this point and this second point here, or the slope of this line. I'm going to use this point as well. What's point 2 then? What's the coordinates? 10, 0. Right, remember we always do the x or the horizontal quantity first. So 10, 0. All right, so we said that the slope is the same as the rate of change, and that is the change in y divided by the change in x, right? Or rise over run. When we calculate rise over run or change in y, what we always do is we always take the difference in the y values and we always start with y2, okay? And I'll explain why this is. We always start with x2 here. So the change in y is this vertical change, and really I'm trying to find the vertical change between the vertical sort of measurement at this point and the vertical measurement at the second point here. So you take the final minus the initial, or y2 minus y1. In this case, y2 is 0. You see, here's y2. And you subtract y1. That is the y value for point 1. All right? y2 minus y1. Change in x is this change from here to there, right? That change. So x2 is, here's x2, that's 10, minus, here's x1, the x value for point 1, 10 minus 0. So the slope is negative 1,000 divided by 10. And yes, this negative is important because when we have a slope that goes down from left to right like this, that is a negative slope. Maybe it makes more sense if you think of it as a negative rate of change. So if we finish this off, what is that? That's negative 100. And what would my units be for this rate of change of this plane? What's the vertical units? Meters per minute. Good. So the slope or the rate of change is negative 100 meters per minute. In the context of the problem, you could say that the plane is descending at a rate of 100 meters for every minute that it is, descending. Every minute you go 100 meters, you're 100 meters lower or closer to the lake, right? And again, this is a negative slope if it goes down from left to right. Up here, this is a positive slope if it goes up from left to right. That's positive. This one, negative. That make sense? Okay. So this might be new to you. Let's y2 minus y1 over x2 minus x1. Again, does it matter which one's the second point? Not really. I always take the point that's furthest to the right as the second one, and then the one that's on the left. Okay, so just keep that in mind. Now, you don't have to do this this second little bit here, but I'm going to redo this for you real quick. I'm going to take, like as I promised, 2 different points, okay? And I'm going to do this. So let me erase this too. So point 1 and point 2, okay? This is going to go a bit faster, but watch. Let's pick, I don't know, this one and this one, okay? So what's the coordinates for point 1 here, the first one? That is 2 and 800. See that? This is the coordinate 2, 800. So that means after 2 minutes, the plane is down to 800 meters above the lake. Now the second point is 7 and 2, 3, 4, 300. Does that make sense? 7 and 300. Okay? So again, you can pick any 2 points of the line, calculate the rate of change. So again here, the slope is change in y over change in x, which is y2 minus y1 divided by x2 minus x1, which is, what's y2? 300. What's y1? 800. What is x2? 7 minus x1, 2. So what does that give us? What's 300 minus 800? Negative 500. Good. What's 7 minus 2? Positive 5. When simplified, this is negative 100 and meters per minute. So you should get the same answer. It doesn't matter which 2 points you take. If it's a straight line, you should get the same slope. Okay? Good? Okay, so that's kind of step one. That's a big part of this lesson here for today. It really is. Okay? The second part of this lesson involves sketching a graph of a linear function that's given. Okay? So we are now going to use other features of the graph to sketch. So draw a little coordinate plane graph in your notes like this. Label that x, label that y. Alright, so if you were asked to sketch this, we know that this is function notation, and really this is the same as y equals negative 2x plus 7. Right? Now we talked about in an earlier lesson, we know something about the features of this equation. What is this? Who remembers what this number represents on the graph? What does this number tell us about the line, the graph of the line? Anybody? You remember what that means? Or what that tells us? No? Okay. Any guesses? Yeah. Okay, would it start at 7? Would the slope start at 7? Okay, you're on the right track, I think. Okay, let me go over this again. I just talked about this real briefly in a previous lesson, real briefly. So it's okay if you don't remember. Now, let me just show you this. Okay, table of values, right? Let's do x and y table of values. And if I put in 0 in for x, right, and I want to find its y partner value, what I literally do is I rewrite this equation, y equals, and instead of x, I put in 0. Do you remember doing this? Alright, so what is partnered with x equals 0? That's y equals 7. Okay? In a linear function, if you put in 0 for x, you will always end up with whatever this constant is. And that means that the y-intercept will always be when x is 0, and it will always end up to be this value on the y-axis. So this value right here is the y-intercept, always. Okay, that's the y-intercept. So I'm just going to erase here to leave some room, okay? But that means that you can just look at this constant number, the number that doesn't have the x or the variable on it, and you can go, all right, I'm going to go 1, 2, 3, 4, 5, 6, 7. And here is going to be my y-intercept. I know for sure that that point is on this graph. Okay, that's what you know first. Oh, I know where this was. This was at the tail end of that video that I asked you guys to watch. You guys were to finish the last 10 minutes. Okay? So we talked about this for sure on that part of that video. Okay. What about this part? What does this represent in this form of the line? Anybody remember that? You remember that? What does this number represent? Yep. It's the number that the y value will go down to every time. Okay, so as the x value moves, the y value moves kind of this way because of this number. Yes. Okay. What is that actually referring to? Yes, the rate of change. Okay. It is the slope. This is the slope of the line right here. And we call this form of the line y equals mx plus b. This is the slope y-intercept form of a line. Okay? Because we can easily see the y-intercept and we can easily see the slope. Now if we were to graph it, we take both of those characteristics and we can do this. Now watch. So this is the slope, -2. What does the slope actually, what's another way to put the slope? The slope is, let's just go back here. The slope is actually what? Change in y divided by change in x. What are the two words that we also used? Rise over run. Okay. Rise divided by run. Can we write -2 as a fraction? Because this looks like a fraction, rise over run. What is -2 as a fraction? Anyone? -2 over 1. Yeah, very good. -2 over 1. So guess what? For between any 2 points on the graph, on the line, we know that the rate of change is -2, which means that we would have a rise of -2 and a run of 1 between any 2 points that we could guess on the line. So what you do is you start at the y-intercept, okay? You start at the y-intercept right here. That's where you start. And then you use the slope to plot your next point. What is a rise of -2? What does that mean? Yeah, a rise of -2 means you rise downward, okay? So it's like you're going down. So this is what we do. We literally go 1, 2, down, and our run is 1. So we go over 1 unit. Now I'm going to make my little gradients here, my little tick marks on my axis down here. So my next point that I can plot is going to be right here. I start at my intercept and I use my slope to find out where my next point is. And you can just keep doing this over and over and over and generate as many points as you want. Watch this. Go down 2, 1, 2, and go over 1. And that's exactly where the next point, or one of the next points, would be. So down 2, over 1, down 2, over 1. You see that? And this should make a nice straight line. Now I'm going to just try and get some help here. Okay, something like that. And okay, so the line is sort of good. But do you see how that forms a straight line? Intercept and slope. All right? Any questions about that? Because what I would like you guys to do is to quickly plot this line for me, okay? So y equals x minus 3. Okay, you guys go ahead, take a minute and plot y equals x minus 3. There's a couple things you need to ask yourself. And the first is, what is the rate of change here? It does not appear to have any rate of change. What is the rate of change here? What's the slope? It is 1. Yes, very good. Okay, so go ahead and take a minute to do that. And you should have a graph that looks something like this second one right here. Okay, so here is y equals x minus 3. Now, let's just check the two important characteristics that helped us to graph this. The first one is, this is the y-intercept, right? Y-intercept. So, here's 0, 0. So if the y-intercept is -3, I go down to y equals -3. So 1, 2, 3. And there's my intercept right here. Okay? Intercept right there. That's where you start. When you graph this, you always start at the intercept. Do not start at the origin. Do not start anywhere else. You have to start at the intercept. Okay? Then you can use the slope to plot some more points. And again, the slope, because there's no number there, that means it's 1, which 1 as a fraction is 1 over 1, which means we go a rise of 1, a run of 1. So up 1, to the right 1. Put a point. Up 1, to the right 1, put a point. Up 1, to the right 1, put a point. So on, as many times as you want. Use your ruler if possible. Okay? Always important to have a nice straight line. And graph paper if you have it. I don't know how many of you have graph paper as a notebook. It's a really good idea in math to have graph paper notebook. If you don't, it's not the end of the world. You can see on my screen here, I don't have graph paper, but I just got to be real careful with my lines and with my dots and stuff. Well, I mean, I sort of do, but what I mean is that I don't have the lines all the way in between. Like, you know what I mean? So yes, I kind of do have graph paper in the background, but I still am, like, look at this right here. You see this? Like right there, you see that? I would have to be a little more careful. I should probably be a little bit more careful with those because those are not evenly spaced. You just have to make sure when you're graphing something carefully that you have your points nice and evenly spaced. So yes, you're right, I do sort of have graph paper. But it's really tough to draw freehand on this deal too. Okay, any questions about that? Yes, no? Okay, plotting, important. So if you look at this graph, this is another graph in your textbook. It says this graph shows the fuel consumption, that's how much gas is used, of a scooter with a full tank of gas at the beginning of a certain journey. All right? So again, from this graph, we can tell that at the beginning, there are 8 liters of gas in the scooter. And it says the tank is full. So guess what? We can also say that not only is there 8 liters of gas at the beginning of this journey, but that the scooter's tank has a maximum capacity of 8 liters. Okay? You can get that information out of there too. If it's full, and this is exactly how much we have when we start, then that's the fuel tank's capacity. All right? Now, this intercept over here is 200 kilometers. That tells us that 8 liters of fuel for this scooter should take this person a distance of 200 kilometers. Okay? Now, what I want to talk about, though, are restrictions on the variables. Okay? Very important. And that is restrictions on domain and restrictions on the range. So let's talk about that briefly. You got to consider the context of the problem. So when I talk about restrictions, this is values. These are values that are not possible, okay, or that don't make sense to the question. So, for example, if I'm talking about a restriction or restrictions on the domain, okay. So look at this here. For this situation, all right, for this situation, it's pretty obvious that we start at 0 kilometers. That's where it starts, right? We start at 0 kilometers. What doesn't make sense is to have a piece of the graph go this way for the domain. Why? Because we would have negative values over here somewhere, and if we're starting at a starting point, that's obviously the 0 kilometer starting point. Negative distance going, back before we start the question, why would we? There's no data we can collect there, right? So the restrictions would be we can't have anything less than 0, right? On the domain, nothing less than 0. Because if we're talking about a distance from a starting point, a negative distance in this case doesn't make sense. Now, what else do you notice about x values that wouldn't make sense to this question based on this graph? And look at this number that I circled. That has something to do with it. Okay? Any ideas? Any values for x that we wouldn't really care about or wouldn't really, that are not part of this question? Yep. Okay, look at the graph. Yes, look at the graph. Starts at 0 and goes to 200. So anything above 200 is not part of the question. See that? We're not talking about that. So for your domain, nothing less than 0 and nothing greater than 200. Because for this graph, again, the domain starts here and it ends here. There's no graph beyond that. A scooter with an empty tank will not go any further, right? And we're not talking about pushing it or putting it in the car and driving around. Okay, what are the restrictions on the range then, knowing this about the domain? What doesn't make sense if we're talking about the volume of gas? Yeah. Okay, why? Yeah, it's full. It's full at 8 liters. Yeah, you said nothing greater than 8. That's absolutely right, because it's full at 8 liters, so you can't get above full. So, we would say nothing greater than 8 for the range. Yeah, that's right. This doesn't make sense up there. And what else for the range? Is there any other restrictions or whatever that doesn't make sense? Very good. Nothing less than 0. Why? Because you can't have negative volume of gas in your tank, right? I mean, that would be great, right? You just never fill up ever. How much gas you got left? Oh, negative 1,000 liters. I've been empty for a very long time, and I'm still going. That doesn't make sense, right? So, nothing less than 0. Now, do you remember us talking about the set notation? Remember that? The set notation? So for the domain here, what you would do is you would state only the parts of the domain that actually make sense for the question. So what's the domain in this question? Everything between what two values here? Everything between 0 and 200. Do you remember how to write that? You put 0 here, that's where it starts. And are we including 0? At distance 0, yeah, that makes sense. So we put less than or equal to. Now the distance, we're just going to, I guess look at it, it's d here, right? Okay, so we'll put the variable d. Less than or equal to what? 200, very good. So that's the domain for this question. The graph only goes from 0 to 200, that's all that makes sense, that's our domain. And likewise, the range, right, goes from 0 all the way up to and including 8. And is it, let me see here, v, I guess that's v is the variable, so we'll use v in our statement of range, the volume of fuel. Okay, so there's our domain. The restrictions would be anything that's not in the domain and anything that's not in the range. Those values are restricted. Make sense? All right, the last example we're going to look at in this lesson here, again, what we understand is we know that there's a relationship between these two variables, right? In this case, it's the number of yearbooks and the cost. So if more yearbooks are ordered, the cost is going to go up. How do we know that? Well, these points seem to be ascending, right? They get larger. So as the number of yearbooks goes up, the cost also goes up. That's pretty obvious, right? Doesn't make sense that you'd actually pay less if you want more of something. Okay, so this one says, this question is just a little bit different. It says the budget for publishing costs for this particular school here, all right, so they're publishing a yearbook, College, Louis Riel, in Winnipeg. The money that they have to spend is $4,200. So the question is, and did I get the question? What is the maximum number of books that can be printed? All right? And so this is the data that they've collected. And if you order 0 yearbooks through this company, what's the flat rate that you have to spend? So there's like a base rate that you have to spend in order to get them to work for you. And what is that? It's $500. So if you contract this company and they're going to make yearbooks for you, they have a flat rate of $500 no matter how many you order. Okay? $500. If you order 50, or if they were to order 50, it costs them this amount. What's this? $1,500. So 50 yearbooks cost them $1,500, and so on. Now, would we probably, would it make sense to connect these dots with a line? Probably, right? Let's say we ordered 120 books. Okay? Would it make sense that the cost would be somewhere between, $2,500 and $3,500? Yeah, it would make sense, right? So we could get away with considering this as a straight line. Okay, so that the line would connect them, and I apologize again for my barely non-straight line. But the point is that if they have $4,200 to spend, this is where graphs can be used to determine a whole bunch of information. Where would $4,200 be on this axis? Well, this is 4,500 right here, right? So 4,200 would be approximately right about here, right? Just under halfway, right? Make sense? So if we follow this over, we can determine a pretty close estimate of what this cost would be. And so we drop that down. And so what would you guess the cost to be? Approximately, well, that's 175 right in between there, so just a bit above that. Yeah, you might say approximately, did I say the cost? Sorry. How many books could you get? 180 might be a very good guess there. Okay? So from this graph, we took the data, we continued the straight line, and we were able to answer a question. Now, one more question for you, okay? If the school wanted to order 75 yearbooks, how much would it cost? How much would 75 yearbooks cost? Here's 75. See, the number of yearbooks, you go up until it hits the graph, and then you go straight over, and it would be about $2,000. Do you agree with that? Yes, everybody agree with that? Okay. You get that? Questions? All right. I'm going to give you your assignment here, and I want you to get a start on it. Like I said, I'd like you to do 1 or 2 tonight, and then I'll give you some more time tomorrow to work on it, just the way this class ended here. But here's the assignment for you today, okay? Okay, so you should try and do 4 and 5, maybe for tonight. Get as much done as you can so you can get the rest of this done in class here tomorrow.